Hello everyone. Today I will be presenting my work Atom, a generalizable technique for inferring tracker advertiser data sharing in the online behavior advertising ecosystem. My advisor on this project was Rishabh Nityanand and we both represent the University of Iowa. Ladies and gentlemen, our data is being gathered. When a person visits a website, they are exposing some information about themselves to the online world, such as their likes, dislikes, browsing habits, or browsing history. We call this data gathering. Once gathered, this data can be used for various reasons, but usually it is used to create a user's profile. Now, if there are trackers present on this website, they also have access to this information about the user. These trackers can further share or sell our data to advertisers, who in turn can use this to deliver relevant ads to the user. Now, the problem with our information flowing in such a manner is that this entire portion of the ecosystem is a black box to the user or even the researchers, meaning our data is being shared and we don't know with whom. And there is limited work done on making this black box more transparent in the past. And this work is usually limited by the ad delivery mechanism or it is dependent on an artifact such as the bid value. Moreover, over the last 5 years or so, data privacy policies such as GDPR, CCPA, and CPRA have been put in place with the sole purpose of making this ecosystem more accountable and transparent. However, with limited resources and absence of a generic auditing framework, these policies have not been utilized or enforced fully. Now, if we zoom in on the problem, we can see that the input signal to this black box is the user profile, and the output signal in this case is the ad that we observe. And our goal is to make the internals of this black box more transparent. Turns out this reduces extremely well to a network tomography problem. Now, what is network tomography? Network tomography is the study of a network's internal characteristics using information derived from endpoint data. And in this case, our endpoints can be the user's profile or browsing history and the ads that we receive. Now, theoretically, our problem reduces well to network tomography. However, to verify this, we first use the principles of network tomography to answer the question, can ads represent browsing history of a user? And if true, this means we have a valid and input endpoint, which is the user profile, which represents or influences an output endpoint, which is the ads. Second, using this input-output signal or endpoints, we check does presence or absence of a tracker change the ads that we observe? And essentially this will help us uncover or infer tracker-advertiser relationships. So we ran an experiment to help us answer our first question. For this we needed user profiles. So we trained 7 types of users by instrumenting OpenWPM, which is a web measurement tool. For training each user type, we essentially visited 100 websites that were relevant to that user type. For example, if we were training the games user type, we visited 100 websites that were specifically related to games. Once we had these users, we collected ads that were delivered to each of them. To analyze these ads, we extracted textual information from them and then converted that into a simple count vector of the words. We repeated this process 9 times and essentially obtained a total of 63 users and their ads or count vectors. Now, going over the results from this experiment, we will analyze the following heat map. On the x-axis and the y-axis of this heat map, we see 7 user types that we trained. Each cell represents the count vector of each of the 7 user types, and each of them have 9 entries. So essentially we have 63 count vectors on the x-axis and 63 on the y-axis. For example, if you zoom in on this one cell, this represents one count vector of the user type sports in one run, and there will be 9 of these in this heat map. The heat map itself is based on the similarity between the count vectors we obtain from our experiment. So there are 3 major takeaways we obtain from this heat map. First, we observe a high similarity between users of the same type over time, essentially near the diagonal, where we have similarity between the same user types. On the other hand, we see low similarity between users of different types across time. Basically, away from the diagonal, we see a lower cosine similarity. This indicates that ads of the same user type don't change over time and they are different from other user types consistently. And to hammer in this point, we establish that the difference between the inter and the intra-similarity distributions is significant. So our question about ads representing a user is answered, and hence we have a valid input-output endpoint to our problem. Now let's move on to how we use network tomography and these input-output endpoints to infer tracker-advertiser relationships. For this, let's go back to our reduced network tomography diagram, but with a few changes this time. Let's suppose we only have 3 trackers and 3 advertisers in the world. When a user visits a website, these trackers gather information about the user. After this, the information is out in the online ecosystem, and God knows how it's shared. Finally, out of this black box comes ads from 3 advertisers. Now, our goal is to see what happens in that black box. In other words, which tracker is linked to which advertiser, if at all. Now let's focus on finding relationships of the advertiser X in this case. So in the case where we don't interfere at all, X shows us these ads. If we look closely, these are all food related ads. We can call this the control ads, as we did not make any change to the trackers. Now what happens when we block tracker A? Turns out nothing. We still see the same kinds of ad that we saw in our control run. We record this in a table as we see no difference. Next, we block tracker B. Now suddenly we see ads that are all sports related. So essentially the advertiser now thinks of this user as someone else. We record this as well as seeing a difference in the difference column. We do all possible combinations of blocking and record how that changes the ads that we observe. Using this table, we train an interpretable statistical model that tries to predict the difference column based on the combination of the tracker blocking as a feature. If this model has high accuracy, we extract the most important features from this model, in this case B and C. And finally, this tells us that B and C have a relationship with the advertiser X. Now running this on scale, we gathered the following relationships. The 3 columns on the left denote the advertiser in the first column, the accuracy of the model in the second column, and the inferred relationships in the third column. For example, the first row shows OpenX has a relationship with Oracle and Alphabet. To validate our relationships, we used 3 sources of ground truth. First, we visited the Attorney General's website where data brokers are supposed to register themselves. We explored those data brokers and found and enumerated any disclosed relationships that they had, and we were able to verify OpenX's relationship with Oracle using this methodology. Secondly, we used client-side cookie syncing to validate other relationships, or as you can see, most of our relationships that we uncover in this experiment. And finally, we used header bidding, which is a technique previously introduced by previous literature to validate another one of our relationships. We can see some of the relationships have no way of being validated. Now, we have successfully executed an experiment that helps us infer never before seen tracker advertiser relationships. However, this work is limited in 3 major aspects. Firstly, scale. Our approach does not scale well, as it would require 2 to the n combinations if we're monitoring n trackers, and that number grows exponentially as we increase the number of trackers that we're monitoring. Secondly, completeness of our ads. So we annotate images as ads based on filter lists, which is not a complete resource itself, but it is as good as it gets. And finally, Our add features are extremely simplistic. We only use text. But other complex features such as pixel entities sentiments can be used and they will only improve our performance. Our work shows that by using just simplistic features such as text, we're able to infer relationships that were never seen before. And with that, I would like to make my concluding remarks that we have firstly established a generic framework to uncover data sharing relationships, and that this facilitates the regulatory authorities by providing them a generic auditing framework that they can use to monitor a tracker or advertiser and their relationships, and then hold the responsible people accountable or enforce their regulatory policies upon them. With that, I would like to end my talk. The floor is open for any questions. Thank you.